Alcohols are organic compounds containing an hydroxyl group, OH, bonded to an sp3 hybridized carbon atom. The oxygen atom is sp3 hybridized too. As a result, the carbon, oxygen and hydrogen atoms do not lie in a straight line, and the carbon-oxygen-hydrogen bond angle is very close to the tetrahedral angle of 109.5 degrees. For example, the carbon-oxygen-hydrogen bond angle in methanol, the simplest alcohol, is 108.9 degrees. Owing to the high electronegativity of oxygen, both the oxygen-carbon and oxygen-hydrogen bonds are polar. There is a partial negative charge on the oxygen atom and partial positive charges on both the carbon and hydrogen atoms. This provides electrically charged sites at which many reactants can attack. For this reason, alcohols are frequently used as reagents for chemical syntheses. As you will see in the next section of this lesson, the high polarity of the molecules also affects the physical properties of alcohols.
Using the International Union of Pure and Applied Chemistry system, the name of an alcohol is derived from the parent name of the alkane, representing the longest chain of carbon atoms containing the hydroxyl group. To indicate that the compound is an alcohol, the suffix "ane" in alkane is replaced by "ol." The location of the hydroxyl group is given by the smallest possible number preceding the "ol" in the parent name. For example, butan-2-ol.
The simplest alcohol is methanol, which is a derivative of methane, in which one of the hydrogen atoms has been replaced by a hydroxyl group. Ethanol contains 2 carbon atoms. Starting from propanol, positional and structural isomers of alcohols are possible. Propanol has 2 isomers, propan-1-ol or 1-propanol and propan-2-ol or 2-propanol, the latter known also under its common name of isopropyl alcohol. There are 4 isomeric alcohols which contain 4 carbon atoms: butan-1-ol or 1-butanol, common name N-butyl alcohol, butan-2-ol or 2-butanol, sec-butyl alcohol, 2-methylpropan-1-ol or 2-methyl-1-propanol, isobutyl alcohol, and 2-methylpropan-2-ol or 2-methyl-2-propanol, tert-butyl alcohol. Notice that both butan-1-ol and 2-methylpropan-1-ol contain a hydroxyl group on the primary carbon atom, while butan-2-ol has the hydroxyl group on the secondary carbon, and 2-methylpropan-2-ol has it on the tertiary one. Alcohols are classified as primary, secondary, or tertiary, according to the type of carbon atom bound to the hydroxyl group. Thus, butan-1-ol and 2-methylpropan-1-ol are primary alcohols. Butan-2-ol is a secondary alcohol, and 2-methylpropan-2-ol is a tertiary one. Derivatives of cycloalkanes containing hydroxyl groups are alcohols too. An example is cyclohexanol, which is a secondary alcohol.
Let us practice naming and classifying alcohols according to the International Union of Pure and Applied Chemistry rules.
This alcohol contains 7 carbon atoms. Therefore, its parent name is heptanol. The hydroxyl group is located on the first carbon atom. Therefore, the systematic name for this alcohol is heptan-1-ol. It is a primary alcohol. In the next example, the longest chain contains 6 carbon atoms. The parent name is hexanol. The atoms are numbered in such a way that the carbon atom bearing the hydroxyl group is given the lowest possible number, 2, in this compound. Apart from the hydroxyl group, there are 2 methyl groups, located on the 3rd and 4th carbon atoms. The full name of the compound is therefore 3,4-dimethylhexantuol. This is a secondary alcohol. This alcohol is a derivative of cyclohexanol, containing a methyl substituent next to the hydroxyl group. In the cyclic alcohols, the number 1 is always attributed to the carbon bearing the OH group. Therefore, it is not shown in the name of the compound. Since the hydroxyl and methyl substituents are in a trans position, the alcohol is trans-2-methyl-cyclohexanol, and it is a secondary alcohol. The longest chain in this compound consists of only 3 carbon atoms, and the cyclohexane ring is a substituent of this chain. Therefore, the proper name for this tertiary alcohol is 2-cyclohexylpropantuol.
An alcohol containing 2 hydroxyl groups is named a diol. One containing 3 hydroxyl groups is a triol, etc. In the International Union of Pure and Applied Chemistry, names of such compounds, the suffix ol, is preceded by di, tri respectively, and the positions of all hydroxyl groups are given.
The simplest diol is ethane 1,2-diol, better known under its common name of ethylene glycol. It is widely used as a component of antifreeze fluids for automobile radiators. There are 2 positional isomers of propane-diol, propane 1,2-diol and propane 1,3-diol. Propane 1,2,3-triol is better known as glycerine. It is an important constituent of natural fats. What would be the name of the compound shown on the screen? The longest chain consists of 8 carbon atoms. It contains 1 double bond starting at the second carbon atom, therefore the compound is a derivative of octuene. The geometric configuration at the double bond is trans. The compound contains 2 hydroxyl groups at carbons 1st and 5th. The full name is then trans-octuene 1,5-diol. The high polarity of OH bonds gives rise to extensive hydrogen bonding between alcohol molecules. Hydrogen atoms bearing a partial positive charge are attracted to the negatively charged oxygen atoms of neighboring molecules, forming a network of hydrogen bonding throughout the body of the liquid. For this reason, the intermolecular forces in alcohols are exceptionally strong, since they include strong hydrogen bonding interaction, moderate dipole-dipole interactions, and weak London forces interaction. As a result, the boiling points of alcohols are much higher than the boiling points of alkanes of comparable molar mass. Even the simplest alcohols are liquids at room temperature. The importance of hydrogen bonding in intermolecular interaction is illustrated by the dramatic increase of the boiling points in the order hexane, no hydroxyl group, pentan-1-ol, 1 hydroxyl group, and butane 1,4-diol, 2 hydroxyl groups, all having comparable molar masses. Because the London dispersion forces become stronger with increasing molecular size, the boiling points of alcohols increase with their molecular masses. Alcohols can easily interact with water by hydrogen bonding. Therefore, methanol, ethanol, and propanol are freely miscible with water. As the molar mass of alcohols increases, however, the hydrocarbon portion of the molecule increases in length, and the solubility in water decreases correspondingly. Butanol and pentanol are only partially miscible with water, while from hexanol onwards, alcohols are insoluble in water, and their physical properties resemble more closely the hydrocarbons of comparable molecular mass.